Hello everyone, I want to welcome you today to our lecture series, and in today's lecture we'll be talking about the periodic table 1. This lecture will be divided, because of the volumes, will be divided into a couple of lectures, but today we're going to be starting with the first part of the periodic table. And like I've always said in class, periodic table is a library of elements that basically determines what every matter is made of. Let's see what we're going to gain in today's class, at the end of today's class. So at the end of today's class, we'll be able to do the following: describe the periodic table itself, recognize the features of the periodic table, the organization of elements in the periodic table, recognize the features, and we'll be able to locate elements in the periodic table using the group and the period designations, and we're able to predict something I'm plugging in, which is very important that I start putting that out by now. Predict the number of electrons in the valence shell of atoms of element, which I'm going to explain what a valence shell means in this case, because this is an introductory class. I want to make sure that I will not fall into the trap of making it complex, or on the other hand trying to oversimplify it, but I will do my best in making sure that this information is passed through. Okay, let's talk about periodic law. Again, this is not something I will expect you to begin to memorize, but a periodic law, as it relates to the periodic table, simply states that the properties of elements are a periodic function of the atomic numbers. You know, when we say periodic simply means something that occurs at an interval in a repeated pattern. Whenever there is a periodic stuff, like if something has happened periodically, something that happens at an interval in a repeated pattern. And we'll see this pattern when we look at the periodic table themselves. So chemicals and physical properties of elements will occur in this interval when they are arranged in order of their increasing number. You see, the periodic table is arranged in order of what we call, of course, we've already introduced this, the atomic number of element. Remember, we talked about atomic number in previous sections. Atomic number, which we denoted with the symbol Z, I remember that. Now, these numbers, I've always called them the serial number, or what I call the social security number of elements, because no two elements will have that same number. So the periodic table, on the other hand, is just a tabular arrangement. I'm going to use my highlighter. Tabular arrangement of chemical elements by the atomic number and recurring chemical properties. As these elements are arranged, we see a pattern in each of the groups. And even when you go either down the group or across the groups of this element in the periodic table, you see regular patterns or changes in their both physical and chemical properties. So the structure of the table shows these periodic trends in elemental, chemical, and physical properties. These properties will occur. That's why we use the word periodic. So the periodic table itself is arranged. The periodic table itself is an arrangement of elements based on that periodic law we talked about into vertical columns and horizontal rows. It is arranged into vertical columns and periodic rows. The vertical columns actually are called the groups or families of element or family, whereas the horizontal row, we usually call it the period, which I also tell students at this level. If you don't want to say they call it the period, you can call it or shell. It represents the number of shells. We're going to talk about where that comes from. So in modern periodic table, elements with similar chemical properties, elements that have similar chemical properties, not the same, they will be similar in the way they act. Similar chemical properties are placed in the vertical column called the groups or the families. If you look at this now, let's look at this here. So the groups are the vertical columns. And these vertical columns go from, according to the American designation, 1A, 2A. You see that? This is 3B, 4B, 5B, 6B, 7B, 8B, 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 1B, 2B, 3A, 4A, 5A, 6A, 7A, 8A. So it starts from group 1A to group 8A. We're going to talk about these designations. So these vertical columns are what we call the families of this element, the families of this element, the families, or yes, everybody has a family where they come from, right? Now, the horizontal arrangement is what we call the period. And the period here has period 1 to period 7 of those elements. And this period, of course, goes across from left to right. Okay? Now, in the modern designation of the periodic table, actually, the number used is actually group 1, group 2, that's how it is done, and then group 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Then group 13, 14, 15, 16, 17, and group 18. That is the modern arrangement of the periodic table. So there are actually 18 columns or groups in that modern arrangement, columns or groups. So this is actually the modern arrangement. And you look at this periodic table, there is another group that is placed down here. We call them the actinide and the lanthanide that cannot actually fit conveniently inside this table. They were brought down and they're called the lanthanides and actinides. So now let's talk about the group or the family. Now the US system uses the Roman numeral and a letter, either A or B, at the top of the column for their own designation of the periodic table. So that is the first one that I read of. The IUPAC system uses groups 1 to 18. So in IUPAC system, it is 18 groups of elements. But in the American system, it is group 1. It is group 1 to 8. But in some of them, you have the attachment of 1A or 1B. So elements that are placed in elements 58 to 71 and element 90 to 103 are not placed in their correct order, right? In their correct periods, but they are located below the periodic table. They have been cut out and placed below the periodic table. These elements are actually called the inner transition metals. They're called the inner transition metals. So we'll get to those names all much later. The inner transition elements. That's what they're called. They're placed, moved down for convenience on how the periodic table is shown. So let's take a look at what a modern periodic table looks like. Look at what I made this periodic table myself, but this actually conveys the information I need. So I did it in both of them. The American nomenclature is on, or American grouping is on top. The IUPAC grouping is down. The American grouping is still very convenient, but for the level of this class, for students to actually understand, particularly by the time we start talking about chemical bonds, and this is going to help you make the direct connection. So the top here is the American system. Let's just label it American system. And the one down here is the IUPAC system. The IUPAC system. Of course, IUPAC means International Union of Pure and Applied Chemists. That's the meaning of that. Now, again, like I said, this goes from the IUPAC system goes from the group 1 to group 18, whereas the American system goes from 1A to group 1A to group 8A. Now, if you want me to hand you a copy of this particular periodic table in class, I can. But again, like I said, I try to combine these to let students understand that these two can be used. And however, America still uses particularly the one that goes with the Roman numeral and A or P. So this is what it looks like. This is the full periodic table, just using only the American system of periodic table. And this is black and white. And this is the one I'm going to hand out in class, particularly for you to use. And again, as you can see, usually you have the groups shown. The period is not usually shown, but this is 1, 2, 3, 4, 5, 6, 7. This is usually how it is shown in the periodic table. So let's talk about group and period designations. You see, each element belongs to a particular group and a particular period. Now, if you draw the line where the period and the column meet is where the element. So if you draw the line, if you draw it from the group and then where it meets the period is the location of that element. This will be the location of the element. So every element must be located And it's just like saying there's a city and there's a state where each element is located. So, example, potassium, potassium of course is element number 19. If you look at your periodic table, potassium is this. This is potassium. Here, potassium is located where? It is located where? In group 1A or group 1, and then period 4. So if you draw this line, this is where it's going to meet. That will be the location of that guy. Zinc, on the other hand, look at zinc here. Well, let's look at zinc. This is zinc. Zinc here, again, you can do the location. It's period 4. If you look at it, it's in period 4, but in group 2B. So you can always do this as well to zinc. As well. That is what you have here. Oh, well, we did this already. This is zinc. Yes. So, of course, zinc is number 30 in the periodic table. Fluorine, on the other hand, if you look at fluorine, let's look at fluorine. Look at fluorine here. Of course, fluorine here is group 2A, and then what? Period 2. Look at that. It is located in period 2. Let's look at it. This is it. Period 2. This is where the line meets. And again, that's fluorine, which is fluorine is number 9. And again, if you don't want to say group 7, you can say group 17, just like you have here on top. This is group 17. And then barium, on the other hand, barium is element number 56. So this is barium itself. They're located. This is barium. Okay, let me use the circle. Barium, this is barium. Barium is number 56. And again, barium is what? It's located in group 2. This is it here. Group 2A, or normal group 2. And then period 6, where it meets. So every element has a group and a period in which they are located. And that's easy by the time you use your periodic table to do that. So let's do a reflection. It says identify the group and the period to which each of the following elements belong using the American designation, because these are the common ones you're going to be using mainly in your lecture. So I'm going to stick to using these ones because that's what I'll ask you in exam. Selenium, Se. If you have a periodic table, you go to selenium. See it here. Selenium. So selenium there, if you look at it, selenium is number 34. If you look at it, number 34 is located in what? Look at it. Group 6A and then period 4. So you can always draw your line if you want to do that. This is period 4. So selenium is located. Let's do that. Just located in group. Group 6A and then period 4. Period 4. Period 4. Let's look at V. V is vanadium. Vanadium. So vanadium, on the other hand, vanadium is, you see that? Vanadium is element number 23, of course. So it's located where? Again, period 4. Look at it. This is period 4 here. Period 4 and group what? Group 5B. So I'm going to say group 5B, which is normal group 5. If you want to put that in bracket, I don't know if you want to do that. And then what period? It is located in period P4, period 4 as well. So it's your choice. Element number 48. What is element number 48? What element is number 48? What did you do? You look at your periodic table. Number 48 is cadmium. Element number 48, which is this guy. Again, it is period 5. And it's group what? Look at it. It's period 5. And is what? It is group 2B. That's what you see there. So cadmium element, this element is cadmium. We can write it. It is located in group 2B if you use an American system. If you want to use the IUPAC system, of course, it's going to be what? 12. Group 12. And then the period, again, the period is period 5. And the last but not the least will be element number 35. Element number 35 is what? Bromine. Of course, if you know the element is bromine. Bromine is number 35. Bromine, of course, is located in period what? You see, is located in period 4, of course. In period 4, the work group is located in group 7A. So it's going to be group G 7A. Or if you don't want a 7A, you say what? Group 17, the IUPAC system. And the what period is it located? It is also located in period 4. So every element has a period and has a group in which it is located and the family. So it's important you know how to do this. Now, before we move on, let's talk about, this is very, very important because I want us to understand the concept of valence shell, because in the last section, or 2 sections rather, we talked about different theories of atomic structure. One of the most important structures we talked about is the Bohr's model. The Bohr's model, but this time we want to actually compare that with the modern structure of the atom, which we also talked about. Of course, we know, and if we do understand this structure well, that's going to help us by the time we start talking about ionic compound and the concept of valence shell electrons I'm trying to introduce. So that is what we're going to do. So to understand the location of electrons, of course, we have to review both the Bohr's model and the modern structure of atom. Let's look at the Bohr's model first. In the Bohr's model, or what we call the planetary model of the atom, remember that we call this the Bohr's model or the planetary. The Bohr's or the planetary. It's the Bohr's model or the planetary. What does it say? Just like the word sound, planetary. Let me spell that word well. Planet, P-L-A-N-A. Planetary means is that the nucleus of the atom is at the center, of course, this is the nucleus, surrounded by concentric circles. At these concentric circles, which draw their center from the nucleus, electrons revolves around, just as how the planet revolves around the sun. That's all. So these are the electrons. These are the electrons, and they're moving around the shell. And actually, like we said earlier, these electrons can actually jump into a bigger shell, upper shell with a higher energy, and come down. Now, these shells are numbers. The one with the lowest energy is number 1, number 2, number 3. The numerical number represents the energy level. What it means is that the lowest energy is the one innermost, which is the smallest, followed by the second one, the third one, and it keeps going till infinity. Now, according to Bohr's model, Bohr called these lines, these circular lines, orbits, just like the sun, the Earth revolves around the orbit, around the sun. He called it the orbit. Now, this orbit, let me put, this is the orbit. And the orbit that is outside the outermost orbit, is actually called the valence shell or orbit. The valence orbit or shell, right? And the electron located at the outside of this shell is actually what we call the valence electrons. Now, I have taught this in the past, and it is easier for students to understand it this way. This is very, very correct. But I want to say, okay, the best way to understand the location of electrons, because electrons, after most research has been done in this century and the last century, electrons are not actually located in the orbit. It's difficult to actually locate to locate the position of electrons and their speed at the same time, what is being called the uncertainty principle, and a whole lot of quantum mechanical model that has been done on the structure of the atom. Now, I want you to understand it better by what I'm going to say to the next one, which is the modern structure. In the modern structure, which I earlier said, that electrons are moving around the nucleus in a haphazard manner. And in this case, they make just like a cloud. However, as they move, there are areas that these electrons can be found, which are probability. We're not going to talk about that. There are possibilities. But let's throw away the probability measurement of what they are. Let's pretend that electrons are located in shells. So let's look at it. So this is, of course, the nucleus of the atom. Now, the nucleus of the atom. And then after the nucleus, you get the first shell. So this is the first shell. So let's assume that these lines are just the boundaries between shells, which are actually non-existent in per se when you look at the structure of the atom. So these are boundaries. So look at the first shell, it will be this one inside. This is the first shell. This is the second shell, and this is the third shell. So electrons are actually not located at the boundaries. They're located inside this shell. So the first shell here has 2 electrons. The second shell here has 2, 4, 6, 8 electrons. And the last shell here has only 1 electron. Now, the last shell is the highest energy electron, which is the shell that is the outermost. In this particular shell, electrons that are located in the outermost shell, again, are called valence electrons. And there are electrons that actually go into what? Into chemical reactions. There are the electrons that go into chemical reactions. There are the electrons that go into chemical reactions. So, now, this, again, let me try to label this now. Remember, this will become the valence electron. Therefore, this is the valence shell. The shell that contains the valence electron is the valence shell. I've told you the energy levels of the shells. Of course, this is the nucleus. And then this is called, like I said, this is called the shells or orbitals, according to the modern structure of the atom. But we're not going to use that word because the orbitals themselves simply say they are the probabilities where you can find these atoms. That's what they are. You know, they are probabilities. They are not like I'm representing them, but representing them this way is an easier way of understanding that electrons are not located at the boundaries on the lines. They're located somewhere in the shells, and that place is actually at times not defined because they keep moving around. So in both models, the valence shell electrons can be lost or gained, and the number of valence shell electrons corresponds to the group or family of the element. This is very, very important. So the number of this, now this is sodium now. Sodium contains only 1 electron in its valence shell. Therefore, sodium belongs to group 1 of the periodic table, and in other words, can only lose 1 electron from its outermost shell. It has to lose what it has in the outermost shell. So the both models explain it well, but what I'm going to try to use in this class is that I'm not going to be talking about atom looking just this way. I'm not going to use this a lot. I'm going to try to stick to saying that atom looks this way and let you understand that these are actually not boundaries. Electrons are located in these shells, and these shells have boundaries, and these boundaries at times, to be honest, is not defined. Let us move to the next slide. So let's now talk about the valence shell. It's important to now bring in that one. So the valence shell simply is the outermost shell of an element that contains electron. Now, atoms with the same number of electrons in their valence shell have similar elemental chemical properties, and they are located in the same group. What it simply means is that these atoms are actually the same family. They are actually the same family of elements. So, good example. All of them in group 1 here, all these guys in group 1 here. Okay, let me try to draw my arrow this way. All of them in group 1 here has only 1 electron, in the outermost shell, in their valence shell. And that's why they are in group 1. So that is only 1 electron. Those of them in group 2, so here will be 1, okay, let me just say 1 electron. Here are 2 electrons. Group 3 here is 3 electrons. That's what they have in their valence shell. 4 electrons, 5 electrons, 6 electrons, 7 electrons, and 8 electrons in their valence shell. And these valence shell electrons is what determines the chemical reactivity of that element or in the group in which it belongs. So those electrons are called the valence. So the electrons that are located in the valence shell are called valence electrons. So let's do reflection here, which is a quick one. This is a quick reflection here. It says, using the periodic table to determine the number of electrons in the valence shell of element from group 1 to group 8. Again, group 1 is going to be what? It's important, is 1 electron. Group 2A, of course, is 2 electrons. Group 3A, 3 electrons. Group 4A, 4 electrons. Group 5A, of course, going to be 5 electrons. Then group 6A will be 6 electrons. Let me continue here. Group 7A will be 7 electrons, and group 8A will be 8 electrons. So what we simply need, you see the kind of information the periodic table provide. If you know the group of the element, that group will provide that. Now, there are some certain ones that do not have a fixed or constant number of electrons in the outermost shell. Those ones are these guys. We call them the transition metals because they change, and these ones here. So, but for now, we're not going to be talking about those ones, the transition and the inner transitions. In the context of what we're doing now, we're going to be excluding those two for now, and we're going to get back to them. It says, how many electrons does phosphorus, which is number 15, you can locate phosphorus, is in what? Is in group 5. So it will have what? 5 what? Since it's in group 5, therefore it will have 5 electrons in its outermost shell. All right. And having said that, we've come to the end of this lecture. Thank you for listening. Bye.